My name is Hamid Salehi. I'm the Director of Product at Adaptive and Embedded Computing Group at AMD. We have been involved with providing hardware for ZK proof generation for the past few years and really supporting the community. Last year, we were a technology sponsor for Z-Prize, and this year as well, 2023, we are a technology sponsor as well. So that was a little bit background about me. And before we get started, I want Evan and also Rahul talk a little bit about maybe introduce yourself and then your involvement with on the hardware side, especially with ZK proof generation, and kind of give the audience a little bit background. That would be great. Maybe I start with Evan and then go to Rahul.
Yeah. Hi, everyone. My name is Evan Marshall. I'm the CTO of Demox Labs. Our goal is to make programmable privacy as practical as possible. So we're really focused on client-side proof generation. In that vein, we are one of the architects for Z-Prize Track 2, which is browser-based proof generation, optimizing it over BLS 12, 381. And we're probably best known for our wallet, which is the Leo wallet on the Aleo blockchain with little more than 100K users.
Very good. Rahul?
Cool. Hey, everybody. I'm Rahul. I'm currently at Wormhole, which is a cross-chain messaging protocol. Currently, there's a lot of talk about bridges in the ecosystem, but this is something that we've been working on for a while and kind of moving to a ZK solution as well, and that's really where we're trying to take production ZK into the market. My background, I was involved in Z-Prize last year as a participant. I worked on a FPGA MSM implementation that's out there. You can check it out, called Cyclone MSM. I'm also part of the Z-Prize steering committee this year, and really excited to see kind of the implementations that come out this year. It's more focused on the application side as opposed to the low-level ZK primitives.
All right, very good. So I'm thinking maybe first question we go to Evan, and both me and Rahul are kind of more familiar with the server side as far as hardware acceleration goes. On the browser side, maybe obviously dealing with programming GPUs to accelerate ZK proof generation. How is that different? Comparing it to what we do on the server side, and in terms of developer ecosystem, programming GPUs, type of devices, obviously, what can you share with the audience?
Yeah, so a bit of background. A new standard was released as part of Chrome 1.13 in May of this year called WebGPU. And WebGPU is trying to solve the problem of enabling browser applications to access the GPUs and provide a single universal interface. The language, like Wixel, is most probably closest related to Metal. And it's getting, crypto wasn't the original inspiration for it. It was probably either gaming or machine learning, but it's getting more stable over time as the spec continues to get implemented. I'd say the biggest difference is that you can't really assume details about the chip that you're working on. So a lot of the optimizations that we see in other contexts don't necessarily carry over, but you can still get massive improvements by leveraging GPUs for things like MSMs. So I'd say right now the standard is not fully implemented, but it is part of Chrome Stable. So it is something good to try out, but it's not a lot of the safety features you don't necessarily get. Like right now, you don't know how much memory is currently being used. You basically have to try to allocate buffers and see what happens. So it's still in somewhat of a new stage, but it's a really kind of exciting technology for web applications.
That's awesome. So kind of going back to Rahul, kind of same thing, but on the server side, for somebody who wants to start thinking about doing hardware accelerations on FPGAs versus GPUs, both different primitives, or creating a more complete proof generation. Maybe share a little bit of your experience. Obviously, you participated in Z-Prize last year. Maybe walk us through that process a little bit.
Sure. So the hardware platform that we were at least focused on was the FPGA, like Xilinx FPGAs. So we used, at least for the MSM implementation, the AWS F1 instance, but for the sort of NTT, which is a core part of other proof systems, including Stark's. The C1100 was the provided FPGA. There were a few challenges, obviously, with trying to take some of these proof systems or these primitives onto something like the C1100. Namely, really was like the main issue was really like the data bandwidth issue. Not that the FPGA couldn't compute fast enough, which it can. It's sort of that when you try to move data from your host to the FPGA, if the data bandwidth isn't high enough, it doesn't really matter. If you can do your NTTs quickly, you just won't be able to get the results back in time. So that's something that this year's Z-Prize, and I think lots of folks in the ecosystem realize, and kind of trying to expand the data bandwidth and use better versions of PCIe, which was quite difficult to use previously.
All right, great. And then there was a question I'm supposed to ask myself, basically. And the question is, I presented this morning about different type of hardware, FPGAs, GPUs. And the question is for people who are actually creating proof systems, what do we see as AMD? Obviously, we support quite a broad set of partners, startups that are trying to generate hardware to do. All right. Zero-knowledge proof acceleration. And what we see currently for people who are actually thinking about creating systems that are going to go in production is, and I mentioned this morning, really the mindset have to be, how do I create a complete system where you can accelerate the entirety of the system? Focusing on one single primitive necessarily is not going to help you much, no matter how much you accelerate it. And typically, creating this more complete system that accelerates the entire proof system, first of all, it could involve more than one FPGAs. It could involve a combination of FPGAs and GPUs. There might be primitives that, it's much easier to accelerate them on GPUs, and, certain primitives might be easier to accelerate them on FPGAs. And also, not all FPGAs are equal as well. So you have different types of resources. Obviously, in addition to what you get in terms of fabric logic cells in an FPGA, you have access to different math engines, DSP engines, AI engines. As a matter of fact, there was a very interesting work by Ingonyama that was just released that showed that some of our newer FPGAs that give you access to our AI engines could potentially have significantly better performance compared to previous generation. So really, if you are thinking about a more serious project, creating something to accelerate the proof generation, you have to think broadly as far as how you can accelerate the overall application. We say whole application acceleration, and then what type of resources you need and match that to the available GPUs, FPGAs, and also look at the roadmap, what's going to come out in the next 12 months, and pick the right hardware, because that's extremely crucial to make sure you have really viable hardware acceleration. So now that we kind of got that out of the way, so going back to Evan, so there is a question in terms of, I guess it's a two-pronged question. One is for people who want to get started, especially on the client side. What are the pitfalls? How should they get started? What should they think about as far as developing an application?
Yeah, so we open sourced a repository that was kind of joint work between Aleo and Aztec in terms of like it's called WebGPU Crypto. You can Google it, or maybe I can get a QR code somewhere later. But I think that's a good place to start. You can kind of see that, get some idea of the benchmarks and what it's going to be like. I'd say in terms of optimizing your proof system for web-based clients, it's a really difficult problem in the sense that you don't control the execution environment. So you're always going to need some sort of like WebAssembly backup for if things go wrong in the GPU. I wouldn't rely entirely on the GPU. And there are things that aren't faster in the GPU. So that's another thing to consider. And you also have to consider like the relative power on someone's machine, where if you're dealing with a powerful CPU and there are only GPUs, like an integrated chip, it may not be worth it. So building in the engineering is a really big challenge. It's not just the algorithms, it's, as you were saying, the entire system. And then in privacy applications, things get a lot tougher, but that's kind of I think the motivation for client-side proving until we get some of these fancy MPC networks. built for private proof delegation.
All right, no, that's a very good point. A lot of people ask me, about hardware acceleration, and my first answer is, first you have to establish you actually need it. Because a lot of time, especially with CPUs coming out with 96 cores, you might not even need an accelerator. So you establish that, whether it's throughput or latency, or make it cheaper and establish that, and then figure out how you're going to harness some of the power of GPUs and all the rest of it. It's a great point, Evan. So going back to Rahul, so obviously last year you participated in Z-Prize and to accelerate some primitives and FPGAs. Now this year being part of Wormhole and now thinking about hardware acceleration in a different context as far as for an actual application in production, maybe talk to the audience a little bit about that thought process that, how would you decide whether hardware acceleration is needed or how would you go about it?
Yeah, so I think, first of all, like you guys are both right, which is, first you have to decide whether or not you want hardware acceleration. And, we didn't start in mind with, okay, we're going to take whatever primitives we're building and we're going to hardware accelerate them. I think that's definitely the wrong approach. We built our system, and then we benchmarked it. We said, here's the constraints of our system if we run it on this machine versus this other machine, all CPU based. And we decided, okay, at this point, because our application is extremely latency sensitive, users who want to use this cross-chain messaging protocol aren't going to wait an hour or 2 hours for either for their messages or their assets to move cross-chain. So it's extremely important that in this competitive market where there's lots of different cross-chain messaging protocols and bridges, that if you're going to offer a trustless solution, that it'd be competitive with any other validation mechanism or verification mechanism that's out there. And so if you want to make it as competitive as, let's say, like a multi-sig approach or as an optimistic approach, we really need to be as close as possible to the actual consensus of the relative source chain. And so hardware, I think, does provide a lot of benefits, but it's still unclear, which parts of the proof system, add the most benefit. I mean, you still run into, Amdahl's law, which is, I think, the core crux of trying to accelerate anything, and deciding which components to accelerate is still remains a challenge. Deciding even which platforms to use, FPGA versus GPU. Deciding which components I want to put on the FPGA, which components I want to put on the GPU. That's still also an open question for many applications. And so that's part of navigating whether or not we want to use hardware acceleration for this component, or maybe for signature verification, or maybe we want to use hardware acceleration for hashing. And so there are a lot of trade-offs that have to be kind of defined before you can move forward.
All right, great. Thank you, Rahul. So going back to Ivan, there are questions about standards, right? Libraries, standard libraries, APIs, and obviously the ecosystem right now is quite fragmented in terms of what's available. And for somebody who wants to get started developing higher level applications, it's a little bit of a confusing environment. I'm curious, what's your view of when is the right time to create the standards, and how far are we from it?
Yeah, given the rapid evolution of proof systems, I actually think the fragmentation is somewhat necessary because we don't know what's going to happen. We started with snarks, and everyone likes the constant size proofs. And then for some reason, even though the asymptotic complexity is worse, snarks seem to be faster in actual practice. But the proofs are too large, and now we have folding. And so we may be, kind of going back to MSMs. So no one really, I think, has a good idea of what is going to be the gold standard of a proof system that we can stop innovating on in 3 years, even 2 years. So I think in terms of standards, it's important to have something like Z-Prize, which is kind of always pushing the limit of what's possible. And hopefully we'll reach a point where things are so fast that we won't be like, if a proof takes 30 seconds to generate, obviously we need it to be faster if you're trying to do like a transaction. But if you're going from like 0.1 seconds to like 0.001 seconds, optimization might not be as necessary. So I think standards should emerge once we have more confidence about the direction the technology is headed in.
All right, very good. I'm kind of putting that question to Rahul a little bit differently. Like at Wormhole, when you were thinking about the proof system, what proof system makes sense, how did you go about that process of picking a system?
Yeah, that's a difficult question. Anytime you're building an application that's based sort of on a moving target, right? There's a lot of research that's coming out. every few months or even every couple of weeks on a new proof system that's based on maybe new ideas that just maybe haven't been implemented yet. And so you might start with a proof system that has a great implementation, and then a few months later, there's someone else suddenly breaks through some glass ceiling, and there's something that's 10x faster, that purports to be 10x faster. Now, if you're dealing with this changing landscape, you have to be very careful about which direction that you choose. Otherwise, your project might not exist in 6 months, especially if you're in this competitive market. So how do you navigate that landscape? I think one, you make directional bets on a few different things, right? You don't decide, okay, I'm only going to use this proof system, but you pick a class of maybe proof systems that you think are going to be valuable, and you sort of have to have like an investor mindset when you're thinking about this, which is you're not trying to predict the price of a specific stock maybe, but you're trying to assess where the trends of the market are going. And you can make bets in both directions. And so at Wormhole, I think one of the things that we've really done is make sure that we both have implementations in these sort of Stark-based systems, but also very much exploring folding schemes and the IVC approach to make sure that this actually may be the right system, whether or not we choose to go one way or the other. So we have our feet in two different places, and we'll see which one ultimately wins, and it might be both of them.
Okay, great. And kind of as last question, I'm going to put this to both of you. For somebody who wants to get started in this space, what's your advice? What should they think about, right? For a new project, for example. Now, obviously, both of you can answer on your on the browser side, client side, but also on the server side as well. Maybe start with Evan.
Yeah, I'm really excited about the power. So we build a wallet. We work with a lot of teams that are building dApps, and I'm really excited about kind of the new wave of applications that ZKPs are enabling for consumers. Applications like on-chain credit, things that aren't using off-chain data that aren't really feasible to do right now. I would say the space is so deep and it's such a rabbit hole that you kind of have to determine where you want to go. So if you want to learn the math, I would recommend a textbook called Moon Math. It's a repository online. You can download it, free PDF. It's a great way to get involved in the math. If you're interested in building like an application that uses ZKPs, I think something like Aleo, which has a Leo language, or something like Aztec, which has Noir, is a great place to get started, where you can use some of the benefits without understanding the math. So I would figure out like what level you want to go in at it, and not try to think about all of it at once, because it's too much.
Great. Same thing for you, Rahul.
Yeah, I would definitely agree with that. I think ZK touches almost every area of computer science. Like all the way from like complexity theory to hardware. It kind of goes down the full stack. So it's hard to be an expert at everything. And I think picking one specific or two specific things within that framework is a good idea. There's a lot of good courses out there. I think if you want to go down the theoretical route, there's a great course by like Alessandro Chiesa at Berkeley from his fall 2020 and 2021 classes, which really go through some of the complexity theory associated with ZK. But really, I think if you want to build with ZK, you really just have to get your hands dirty and start writing circuits in whatever sort of language or proof system that you feel comfortable with. I think Circom is a great starting place. Another great option is to kind of use something like Plonky2, which I've been using recently, but I think is a great starting point, especially if you want to abstract some of the sort of circuit components away. But yeah, I think from an application standpoint, like ZK is, I think there's a lot of possibilities, but at Wormhole, for example, ZK really is part of the underlying infrastructure, and so developers and users don't really touch any of that infrastructure. The goal is to make sure that this is if we're trying to build something like a trustless sort of cross-chain messaging protocol, that it's there and that users don't really have to interact with it. So I think you can work at any level of abstraction. In some cases, even if you're using applications that are built on ZK, you may not even have to touch the ZK components. You can just sort of use and develop on top of that protocol as you wish.
All right, great. So we have a few minutes left in our session. I'm going to open it up to the audience, see if anybody has any questions about. Okay, I see a couple of hands.
Which high-level programming languages or which high-level programming languages or the ZK domain-specific languages do you recommend for programming language enthusiasts or functional programmers to get interested in?
So Rahul, you kind of touched based on it
Sure.
a little bit. Maybe expand on it a little bit.
Sure. So I think everybody's sort of familiar with Circom, which is a great, one of the earliest ZK DSLs that's gained a lot of traction. I think that's a good one to start if you want to understand the sort of how a circuit is, or the programming model for a circuit is very different from maybe other programming models. There's also some newer ones out there that are quite interesting. There's Noir. There's a bunch of these other sort of DSLs, like Aleo has written one as well called Leo. Personally, I think there's another one that I think is quite interesting, which is Lurk, which is more functional based. It's a Lisp. I think that definitely has a lot of promise. It compiles to or interprets to Nova, which is one of the newer folding schemes. So that there's a variety of them out there, but pick your poison and get started, I guess.
Yeah. One other thing I recommend in terms of just learning material. So Berkeley has a very interesting MOOC, massive open source course that's available on YouTube. So definitely worth a read for sure. Okay, I see one more hand, two more hands. All right, three. Okay, that's good. We have.
Yeah, Mike. Hello. Yeah. So I have a twofold question. One is targeting you, Hamid, for AMD. I know AMD has done a very good job in designing or coming out with latest Zinc FPGAs targeting applications, signal processing applications. I have designed millimeter wave radios using your Zinc processor. So now having this looking into the ZK market, if Xilinx or AMD is thinking about coming out FPGA devices specifically targeted for that segment. And second question for all three of you is for people like I design is mostly in system Verilog. So what is your advice into getting hands dirty into this segment?
All right. So on the AMD piece of the question, I guess, overall, there is a little bit of rush to having a specific devices, whether it's ASICs or whether kind of a specific FPGAs targeting a certain applications. Typically, we are very cautious when we think about, a domain-specific piece of hardware. As a matter of fact, we did launch a domain-specific piece of hardware last week and a couple of weeks ago in New York and London, targeting specifically the electronic trading market. But typically, those type of decisions require really massive business cases. The matter of fact is AMD has a very robust roadmap of GPUs and FPGAs that have different combination of resources. And I think within that broad product portfolio, you should be able to design your system, get it to 99% of where you really need to get. So do not focus on a specific hardware, right? It's easy to think about it. It's kind of fun, for raising money, that sort of thing. But it's a very dangerous space to be in unless you absolutely know what the target is and, there is product market fit. So I would caution people against that. And the second part of the question,
could you repeat the second part?
I design FPGAs and ASICs and stuff, system Verilog, and I'm very interested into this ZK proof market. So what would be your advice to get hands dirty for FPGA and ASIC designers?
So maybe I should
writing system Verilog code.
Okay. I thought you were asking about how to use high-level programming languages. So being an FPGA designer, it makes it a little bit easier because if you can work with the circuits, you don't need to go to higher-level programming languages. But frankly, I would say that partner up with somebody who understands the broader system, right? Do not go all the way. You really need a team to develop a lot of these systems. I think the level of complexity is not something that, an FPGA developer can sit at home and develop the whole system. So that's my advice. Have somebody that understands the cryptography behind it, the higher level, primitives, and then you can do the hard work of turning that into hardware, very like VHDL type of language, right? Any other questions?
I have one question regarding to the security of Zero Knowledge Proof. Actually, upgrade the hardware to minimize the impact of the attack or like migrate the vulnerability of the hardware is very expensive. So what do you think about that?
Okay, the security question. Evan, that's a good question maybe for you. He's asking about the security of, ZK systems and,
Yeah. So generally, people target about 120 bits of security, and it's based on the discrete logarithm problem. You'll figure out how big your field needs to be. Most people try to fit their field within, 256 bits. Like BLS 12377 is, a 253-bit scalar field where the MSM, the twisted Edwards field where you actually do the MSM. So that's kind of what people target now if we have to use bigger fields because new attacks, new algorithms to calculate the discrete log become more viable. You can use larger fields. I think there's a big question about quantum security, right, where we're sure that discrete log is broken in a post-quantum world, but none of the internet is post-quantum right now. So it's kind of, I think, a big question of what, cryptography is always designed in such a way that you don't want to overbuild things because then it becomes inefficient, right? So you target specific levels of bit security in such a way that you can still do things efficiently. So if new attacks come up or computers get really, really fast or FPGAs get really, really fast, we'll use bigger fields.
All right, okay.
My question is to FPGA designers. What are problems and is it possible to build FPGA not for a proving system but only for primitive operations such as multiplications and hashing only and let the developers use them in some effective way? Why such a generic devices doesn't exist now?
Yeah, maybe Rahul, that would be a good question for you.
Yeah, I think previously a lot of people focused on like taking primitives like multiscalar multiplication as an example, or like NTT, which are two sort of core primitives, both for different proof systems. But if you really want to accelerate your whole system, which is what I think what Hamid was talking about earlier, it's important that you take the whole take the whole proof system and put it on there if you want to sort of get the maximal benefit of that. If MSMs are 80% of the computation of a proof system and the remaining 20% aren't MSMs, there's something else, and you accelerate MSMs as fast as you want, you'll still run into Amdahl's law. At some point, you won't be able to accelerate your system further. And so if you can put more components of your proof system on hardware, the better chance you have of actually getting better performance. So that's why there's really a push to get all these different components like LDEs, NDTs, other things on FPGAs.
Yeah, thank you.
All right, maybe one last question. We have 1 minute. All right, there you go. I see one in the back.
Hey. Since you've all worked with the hardware, I was wondering what, for you, the ideal hardware would look like, both in terms of programmability and in terms of parallelism or performance.
Yes, obviously, that question, depending on you're on the client side, it's very different versus the back end, right? Maybe for you, how would that look like on the front?
I would like to see the web GPU standard fully implemented on browsers and not just the subset that currently is supported. In terms of actual, it's really a question of a bunch of things, right? So what sorts of proofs are people making on phones versus laptops? Right? And honestly, I feel like machine learning, the hardware requirements that AI is pushing are actually really making cryptography, like more complex cryptography possible on client devices. So I'm more like just thankful we can ride that wave than asking what more I can have. There's like specific features though, like I'd like to know how much memory is currently allocated on someone's GPU and not just like try stuff, because if you allocate too much and crash someone's GPU card, it takes down the whole machine. Yeah.
All right, great. So with that, we are out of time. Thank you both, Rahul and Evan, for 5 more questions. Okay, we have more time. So maybe Rahul, then maybe you answer that same question on the server side as well. That would be.
Yeah, I think there's a ton of things that you could potentially want, but one of the things that I think could be exciting is to essentially have infrastructure or abstractions to help you access accelerators like in the cloud. And I think Ingonyama released something a few months back as well, which was quite interesting. But having access to these accelerators in the cloud really makes it easy for people who want to use ZK to really just plug into some accelerator in the same way that developers maybe spin up an EC2 instance right now. If you have the same sort of approach, it becomes easier to just embed accelerators into your project.
Yeah. And I'm going to answer kind of a tangential, I guess, answer to that. Specifically in terms of FPGAs, until a few years ago, it was very difficult to actually access FPGAs, especially for a startup, people in the community. Back in the day when Ethereum mining was all the rage, people would know, obviously, GPUs you could go buy off the shelf, and FPGAs you could not access unless you knew somebody who knows somebody type of situation. And we did a lot of work trying to change that, starting with Z-Price, for example, giving people access to FPGAs, and now continuing that through 2023. Our goal is for anybody who wants to access FPGAs, even the smaller startups, to develop, any type of applications. There is a path for them, a path that's affordable. Also, we do a lot of community support. So we do provide hardware to a lot of startups that we think has potential to produce something valuable. So we have done, I guess, a lot actually as AMD to really foster the ecosystem. Okay, so more questions? We got a little bit extra time. So, all right. I think
Yeah, the timer here just keeps resetting.
Yeah.
So we're like watching it go down,
Yeah.
and then it adds 5 more minutes.
All right. So I guess with that, we are going to give everybody a few minutes. All right. Thank you, Ben. Thank you, Rahul.
Yeah, thank you.
Thanks.